Qiang and I were contemporaries in our graduate school days. We were friendly competitors in superconductivity. After he graduated from PhD in Iowa State, at the time a very strong superconductivity program there, he joined Brookhaven as a postdoc, then stayed there. Now he's the head of the superconductivity program at Brookhaven. So for all the graduate student who wants to look for jobs, that's where the federal jobs are going to be. Qiang did his both PhD and postdoc work in type 2 superconductivity. Today he's going to tell us about the chiral magnetic effect in condensed matter.
Okay.
Welcome.
Thank you, Sean. Thank you. Well, it's a great honor for me to be invited to give this colloquium. And particularly, I'm pleased not only I met a lot of faculties today, and also my daughter's over there, and she said she's going to try to embarrass me. She's a freshman enrolled in the Brown, so I'm very happy to be here today. So I'm going to talk about the chiral magnetic effect in condensed matter. Now, the chiral magnetic effect is a dramatic consequence of chiral anomaly in a Dirac theory or relativistic quantum field theory there. It is in intensive studies now in the nuclear particle, particularly high energy nuclear physics world for the Quark-gluon plasma in the relativistic heavy ion collisions. Now, 2009, there's a big news over there, and that is the reported evidence of the chiral charge separations by the STAR collaboration of the Brookhaven's RIC program. And that generated a strong interest in the scientific community and the mediums covered by New York Times, US Today, and Newsweek. So the reason is that the chiral magnetic effect is believed to operate at the beginning of the universe and also play a role in other cosmologies, for instance, explosions of the supernova, and also the possibly providing a mechanism for the positive kick. But today I'm going to talk about this chiral magnetic effect in condensed matter that has been discovered, and actually in the last couple of years. So because this concept is quite not so common, so I will start with something we know very well. So that is electricity. I think everybody knows that. Okay. The reason I do that way, go this low, is that early days is that I try to help you, some of the students, to understand, appreciate this chiral magnetic effect in condensed matters. And I'll bring some of the common things we know for many years and to draw some comparison and to see how this chiral magnetic effect can be potentially be a driving force or disruptive force for the 21st century technology in electronics and optics. Now, we know that we own today's world to a man did experiment in the summer of 1831. That's Michael Faraday. He's the one who actually, together with Lenz, discovered electromagnetic inductions. That is the basis for the electricity generators. If you have a closed circuit and you change the magnetic flux inside, and you generate electricity, right? That is the basic how you generate electricity in a machine. Now, several years later, or maybe 10 years later, and it was found that the electricity produced heating. It's called resist heating. Now we also call it Joule heating there. And this is interesting, okay? Because this tells you that electricity passing a circuit has a resistance, okay? And actually, much earlier, in 1827, and the relation between the electric resistance, electric current, and voltage has been formulated in Ohm's law there, and it's expressed here. Now, in terms of today's language, we say that a resistive heating is an irreversible process. Once you generate heat, you have increase of entropy, right? According to second law of thermodynamics over there, this process is not reversible, right? It generates error of time. So this is dissipative. Now, if you have a process which does not break Now we call the time reversal symmetry here because the reverse times is not the same for the resistive heating. Now, if you have a process is totally reversible, then you can reverse it in time. That means it does not break time reversal symmetry over there. There should be no dissipation because there's no entropy change. So in that sense, that if a process does not break time reversal symmetry, then it intrinsically could be a dissipationless. And that's something I want you to keep in mind for our students over there. Now, this has been known for years, but we actually don't know what's actually happened inside. What is the carrier for electricity? That's until 1897 when Thomson discovered electrons. It turns out that the electron is the carrier for electricity. Right? Now, the microscopic theories come up a few years later by Drew. He said that if you have electrons moving in the metals and they will hit something, like defects, and also lattice, okay, and you will produce resistance. Any non-zero temperatures, thermal energies will result in the vibration lattice, and that's the phonon, right? You quantize it as a phonon. So electron phonon is always there at a non-zero temperature, and it will always have resistance. That perception has been there for quite some time. But however, 10 years later, it was found that you can actually have something which totally have zero resistance, okay? And that's superconductivity. It was discovered by the Dutch physicist Kamil Onis. He found that if you have, during the experiment, you study the resistance of mercury, and you cool it at the temperatures close to liquid and nitrogen, liquid helium temperature, 4.2 Kelvin, you found that resistance totally disappears. It's not just small. It is actually zero in today's world. We understand that. So this is called superconductivity. Superconductivity is the backbone for the MRI machines. And there's a superconducting magnet for the various accelerators there. Now, because the piece of superconductor wires can carry 100 times more current as compared to copper wires over there. So in last 10 years or so, I have been involved with the development of some of the high temperature superconductors and in the electricity generations, transmission, and storage over there. Now, this is actually not many material can do that. You can do all these things, storage, transmission, and generations. A superconductor can do that. And I have been involved with this development of cements, superconducting magnetic energy storage device. Basically, if you have a coils over there, because there's no resistance, if you lock in the current in the coils there, the current will be there steady forever, as the energy is the magnetic field energy over there. So it's like a battery, but this battery can last forever, right? But if you someday you want to use it, you open up the switch, you can drain the current out, and the draining of the current is very fast. So this is very good for the energy storage. You can make the coils as a magnet, and you can drive a machine, this rotary machine. For instance, I led a program on the wind turbine drive. We developed some of the coils for the 10 megawatt electric machines for the wind turbine generators. And also, of course, transmission. You transmit electricity without resistance is great. And that's always the high temperature superconductors. But if you look at this axis, this is not really high temperature superconductors. This is still at the liquid nitrogen temperature for use, 77 Kelvin. When we talk about high temperature, people were thinking about something on your furnace. That's really high temperature. We don't even have a room temperature superconductors these days, right? So, so why we don't have a room temperature superconductors over there? Intrinsically, our superconductors is pretty weak. Okay. The microscopic understanding of the theories took many years. Okay. The first come in 1935. London brothers put the two equations. This is phenomenological equations to show the behavior, electromagnetic response in the superconductors. First equation described the ballistic acceleration of superconducting currents by transit electric field. The second one described the Meissner effect there. Okay. Now, the microscope describes what happened to superconductivity is that it turns out the electron does not work in by itself, does not move in by itself individually. They have to form the pairs. And we know that the pairs is called Cooper pairs. That's your faculty, right? So that's the Cooper pairs. They say that because two electrons have the same charge, they will repel each other. You want to bring them together, you have to provide some of the glue, right? So this is glue. But the glue is very weak to bring two electrons together. So, and also, even though you have the Cooper pairs, this is the boson there, you not naturally have a superconductivity. So then I have an opportunity to talk to Jim about his superconductor metal insulating superconductor insulating transition over there, you have this boson. If you don't have the global macroscopic coherence in the ground state for the condensate states over there, you still have dissipations. So it's only that you have this condensate state over there, you can have a superconductor. It turns out that all the Gruiswick condensate state very easy to break up by the thermal energy excitation over there. So that's why it's difficult to get room temperature superconductors. Okay. So then the question is that, is there any other ways to transfer charge without dissipation? And can you do that at a high temperature, possibly at room temperature? And if we can do that, of course, that's going to be disruptive technology to take on many challenges we face today. So this is something is really inspires to see. And then people try to do that. And we don't have much success until last 10 years or so. Even though some of the theories is there, and prediction there, and experiment that actually show up is that there are, at least I can show the two of them. It turns out the edge state in topology insulators, it's possible one way to transfer charge without resistance because those states are protected by topology over there and backward scattering is limited. Okay, sometimes it's totally blocked. Okay, however, this is the edge state is the same thing that if you have bulk material as the insulator edge on the surface is conducting, the cross section is not that large, right? If you want to transfer massive amount of current, it's difficult just from the edge or surface. You want to have a bulk, right? The bulk states actually happen in the chiral effect. And this bulk states can be used as a way to transfer the charge without resistance and possibly the higher temperature. And that's the topic I'm going to talk about today. So I hope I gave you some of the background to show that if we can understand this chiral effect and we can use it, it's probably revolutionary. Okay. So and all these things actually have something related to the Nobel Prize winner here today. And they are all the topological phase transition here. It is protected topology. So go back to the 2016 Nobel Prize over there. And all these effects today show that it has a lot to do with topological phase transition here. Okay. So what is the chiral effect? And this concept is coming from the relativistic quantum field theory. It is the generation of electric current by the chirality imbalance between left-handed and right-handed fermions in the magnetic field. Fukushima and Quasi formulated some of the things for Quark-gluon plasma, the CME or chiral effect over there. So Karzev is a collaborator with me, and I'm really happy to have him around because I can learn a lot from him. So if there are some things I can understand in theory, I can have someone to ask for that. If something theory goes wrong, or I couldn't answer the questions, I will ask the guys, ask Dima. Don't ask me because I'm an experimentalist. So that's very nice to have such a collaborator there. So now this equation shows you that it's a very simple equation, right? This is vectors and it's a scalar there, right? And it shows chiral. This equation actually is very unique. Okay. Now if you look at time reversal symmetry here, I just simply put it here. What you do here is that you do a time reversal, you change it from t to minus t, and if you look at the ohmic conductivity, and the equations change it to the minus here. There's a minus half here because J is T odd and B is T odd, E is T even there. You just do the time transformation. And that breaks the time reversal symmetry, right? It's right there. And it's dissipative, I already told you. If we look at the first London equations over there, it does not. Okay. This is invariant in the time transformation over there, and it's non-dissipative. And if we do the chiral effect the same way there, it does not break time reversal symmetry. So this one is not dissipative. Now how are we going to get it? I told you that you need left-handed and right-handed fermions. Okay. Now this left-handed and right-handed fermions is coming from the high-energy nuclear physics world. It's called massless fermions. And it's actually happening in those Parity ARPES systems over there. I'm not going to talk about this stuff there. This is too hard. I couldn't even understand it if it's some of the high-energy nuclear physics theory there. Now, what actually happens is that if you have particles accelerate at the speed, to the speed of light, or close to the speed of light. And the relativistic quantum field theory tells you that the spin of that, and the spin for the people don't understand the fermion, is that the spin half of charged particles. It will gain chirality. The chirality in this here is defined as this way. They have only two choices, either parallel to the momentum directions, like here we call it right-handed, or opposite. Okay, so there's two choices, the chirality in this massless fermion there, and when you accelerate it at the speed of light. So you have that in the Quark-gluon plasma, right? In the relativistic high-end collisions, that you will generate a lot of quarks, right? Quark is the particles that made up the protons and neutrons over there. They are fractional charged. And you have that. In the condensed matter, we don't have it because we know that nothing really in your phones is running at the speed of light, right, except your light over there, right? But anything in there is not at the speed of light. So you don't have this massless fermions in your condensed matter system. But you have analog of that, and which I'm going to tell you a little while later. Now, in terms of this ones, you have the massless fermions, and if you can provide a strong magnetic field, you will have to see the charge separations. Right? If you see the charge separations, you see the chiral anomaly, and that will indication something to the chiral magnetic effect. And this is very much intensively studied in the heavy ion collisions, relativistic heavy ion collisions. This is the one I told you very big in 2009. They see the parity violation of it for this during the collision of it. Right hand, left hand, they're not equal now. So this is coming from. The reason for that is that during this collision, if the off-axis collision during the heavy ion collision there, and they can produce intensive magnetic field. This magnetic is 10 to the 12th Tesla. It's highest ever you can produce on the face of the Earth. So you have very high magnetic field, and also you have a bundle of extreme relativistic quarks, right? Those are the charged massless fermions there. And you should see that. That's what they're saying, this separation of that. And later on, 2014, and they showed further evidence of that. 15, they showed further evidence during the collision of that. Okay, now we'll finish this with nuclear physics stuff. Go to the condensed matter. I told you I don't have it. I don't have the particles run that fast, right? So what I have, we don't have this systems until it lasts about 5 years or 4 and 5 years until we see a system we call 3D Dirac semimetal. I will tell you this in this system there, you can model it. You can model the systems as if in heavy the massless fermion in the Quark-gluon plasma. So, and also I want to tell you is that I talk to nuclear physics people, folks there. They will say, your condensed matter is not really look at the electrons, photons, or anything. In the nuclear physics, they really look at the single ones, right? They have the particle, real particles. We don't have it. And a lot of times in the condensed matter, we look at the quasi-particles. What is quasi-particle? It is the galactic excitations over there. Electrons in your solid, there is actually not just free moving around there. They are dressed up, right? That's because there's interactions. Interaction with lattice, with interaction with other orders over there. So that's give you effective mass. So we call those things the quasi-particles. Okay, that's chiral particle. Now, do we have chiral particles in condensed matter? Actually, we have it now. So we have 3D semimetals. If you have the 3D semimetals with the quasi-particles that have linear dispersions, then this, you can describe it in a Dirac equation now, analog to the Dirac equation. And that opened a fascinating possibility to study the quantum dynamics of relativistic field theory in condensed matter. So now I will say that we can do some of the experiments on the benchtop, right? Those guys in the meta may say, nah, we still want to build an accelerator, right? But at least we can model that in this condensed matter system now. Yeah.
So the semi-metal has a strict definition as Fermi surface?
I would explain it right here. Okay. So I know that some of the people were asking, what do you mean semi-metal? We learned about a metal insulator, semiconductor. What is a semimetal? Now I show that. Metal, we know that is a partially filled band, right? This is the Fermi surface of there. This, in this case, the conducting band. If you have insulators, it means that the valence band is completely filled. The conducting band is completely empty there, and in the regular temperatures, excitation is energy is too small to overcome this gap, so it's insulator. Now the gap is very small there, and appreciable amount of thermal energy can excite the electrons to the empty state here, then it's become semiconductor, right? Now, if you have these bands touching together, it's called semimetal. Okay, this is semimetal. The semimetal difference between semimetal and metal is that semimetal has a very small Fermi surface, right? Because that's on the tip of that, right? So, and the metals, you have very large Fermi surface. You have a lot of carriers. Semimetal, you don't have a lot of carriers. Okay.
Solid state physics.
Yeah.
In our 241 here, we teach our students that every time when you have a situation like this, when the two states have the same energy, then the perturbation tells us that this degeneracy will be broken by perturbation.
Yeah.
And so what's preventing?
This is at 0 temperatures. Okay.
But even that at 0 temperature.
You could.
Yeah,
you could. This is just schematic to show that. Okay. Okay. That the question you have there is a little deeper than the schematic things can tell you.
So in this case, do they have the same momentum in the momentum?
Do they means what do you mean they?
The valence band and the conduction band.
Yeah.
The bottom of the
Right.
conduction band and the top of the
Valence band.
If they're in the same place in the momentum space, if
Right.
they're touching,
Right.
then perturbation theory says you can't.
Well, yeah, you could. Some say there's an open the gap over there, but this way, this touching over there is really a very small tip over there. Okay, you can see that, right? It's really, cartoon. This is part. Bismuth has shown that. There are a lot of other things. Half-Horslers also show that. I will show that there is a fully semi-metal behavior there. Now, next one, I will talk about the quasi-particles. Now, I'm going to show you this one actually taken from the science paper over there. It's quasi-particle zones there. Now, in the condensed matter over there, we will deal with Schrodinger fermions, right? Because we're not dealing with relativistic particles here. In the Schrodinger fermions over there, Hamiltonian is written very simple, right? This is the energy proportion to the momentum squared. This one we call the dispersion. And this is energy, this is momentum. It's parabolic. So everything we deal with is a parabolic dispersion of that. And here is that we call the electron dress up. This is effective mass here. Now, in the ultra-relativistic direct particles over there, the Hamiltonian is written as here. Okay, this is equal to c, speed of light, Pauli spin matrix, and this momentum. So energy and momentum relation is linear dispersion, linear behavior there. So this is linear dispersion. You want it, okay, to have it. So we have it. Actually, we don't. We have it. Now, if you describe some of the excitations in a condensed matter over there, you don't have the speed of light for the quasi-particle, right? You have a Fermi velocity for those particles, right? So we can model this Hamiltonians and as this way that replace the speed light with the Fermi velocity of the quasi-particles, and this is the pseudo-spin matrix of it. So you have the same things. If you have this linear dispersions for the 3+1 space and time, and you would gain the priority. And by the way, the one I told you that the theory only tells you gain the priority is only for 3+1 space-time. It's even. Okay, if it's odd, like 2+1, it doesn't have a priority over there. It has it. Now, do we have this systems? We know that. We know graphene has it, right? Graphene has this direct cones, linear dispersed behavior over there for the for the fermions over there. But however, a 2D system of it does not have the priorities. Okay, that's just simply based on the theory. You ask me why, I don't know, because that's what the quantum field theory, relativist quantum theory, tell me that. So now, if you go to 3D, so then you will gain a priority. Right? Do we have it? And we know theory has some predictions, but only recently it was discovered that you can have a real material which have linear dispersion, and it is a 3D semimetals. Now, example I show here, there are two types actually. I told you that you can have left-handed and right-handed particles. if they occupy different cones, and that means they are non-degenerate bands over there, it's called a Weyl semimetal. It's Hermann Weyl, he formulated the 2x2 Hermann equation to describe neutrino. At the beginning, he was doing that, but now we use that. So basically, it says that you have the cones will be occupied either by left-hand or right-handed ones, and this is the Weyl semimetals. But if you have a system over there, and the left-hand and right-hand ones occupy the same cone, this is degenerate. And this is called Dirac semimetals. Okay. So actually, in a magnetic field, or you break the inversion symmetry of that, you can actually transfer a Weyl point into the two direct points. Actually, they split. Okay. So each direct point each Weyl point is a singularity in a curvature in a momentum space, representing a magnetic monopoles there. So the Weyl points always come out in pairs. Okay, direct cones is a single one, but in prime magnetic field, it will automatically transfer into the Weyl nodes, a pair of them, because they break the time reversal symmetry right there. So you have the system there. Then how do you measure it? How do you know that you have a system, have these dispersions? Experimentally, there are different techniques. One of the well-used one now is the angle resolved photoemission. Okay, this has been done at Brookhaven. So it was
I thought it was discovered in Beijing by the group.
No, this is on superconductor. This one, angle resolved photoemission, and the one the Buckley Prize, right? So that was developed much earlier. Okay, much earlier in the 90s, become very popular. Was study high temperature superconductors. Okay, so the idea is this way. How are you going to study this dispersion over there? If you have a photons, basically send energetic photons over there, you knock electrons out of your materials, and you have a detector collecting these electrons, you can measure the energy, right? If energy is high enough, knock the electrons in the core levels, you got a peak here. And if you knock the electrons in the valence band, you have this hump here. So this one tells the energy relation, right? But if you spin this detectors in the top hemispheres, you collect the momentum information, right? So if you have the energy and momentum informations, you can get the dispersions of that, right? So that's why ARPES become very powerful tools to study the band structure of a materials, that because they provide both energy and momentum relationships. So this the one I just show you. This is the one we were studying, high temperature superconductors over there. Okay. So the material we studied is zirconium pentatelluride. And this is the single crystals. It look like needles, right? The people look at this one and say, gee, this one doesn't look like 3D, right? So this is like 1D stuff. And you look at the crystal structure over there, and you find that in this zirconium pentatelluride, the conducting channel is really a tellurine chain here. And these dimers form sideways and form a plane. Then they stack together by the van der Waals force. Okay. So you will say that, wow, this one can hardly be a 3D system over there. However, if you look at the ARPES, angle resolved photoemissions, and you will find that, yeah, it is a 3D Dirac semimetals. Now here I show you is the ARPES spectrum over there. Now this one is collected along the chain directions. Okay, you can see the states forming. As you see, semimetal is a very small Fermi surface. It's whole-like Fermi surface state and linearly dispersed. I think this one died. But anyway, you can see linearly dispersed in the figure C over there, and this very sharp feature of lines over there. Now, if you look at the figure A over there, you also see the linear dispersions over there. Figure A there, okay, over there. But this goes this way, right? So in this course, but then you can do that to the close cuts for the photoemission. I didn't show here. You also see the linear dispersions, and also the speed of the particles for this particular one is very fast. And that's can calculate from the speed of the dispersion, the velocity of that. And the Fermi velocity for this state is actually traveling at 300ths of speed of light. It's very fast because the cone is a very steep cone there. So now we know that it's a 3D Dirac semimetals. And the question is, how do you know is there current magnetic effect there? So what is the evidence? What's the smoking gun to show there are chiral magnetic effect in this system over there? So here I'm going to give you a one slide to summarize some of the. Okay, great, thanks. So to summarize some of the events in this field and tell you what we actually see. So the chiral magnetic effect actually is one of the chiral anomalies, and it is known in the late 1960s, and it was discovered by the Adler, Bell, and Jaguar. It's called the ABJ anomaly over there, and that's the time when they found that neutron pions decays a lot faster than charged pions, and that's a anomaly over there. Okay, so, and it is Nelson and Inomiya's, they actually demonstrate the similarities between the fermion systems of lattice gauge theory and electron systems of the crystals. Okay, they were looking at a semiconductor they call the zero bandgap semi, basically it's a semimetals. What they found is that in these systems over there, you can model it as a Weyl system, okay? And if you have a magnetic field applied in the systems at the lowest Landau levels, and you can have a linear dispersion, if you have a linear dispersion band right here, and apply electric field, and this will provide a chiral source to it. And this will create an imbalance. Now, if you have the imbalance of that, you will have a chiral magnetic effect. Okay, I will explain to you a little bit later over there. And how do you measure that? How do you experiment to see that? Actually, Sang and Spivak and Burkov put up theory to show that in this case, in the Weyl metal there, you can have a negative magnetoresistance. I basically tell you that your conductivity goes up, right? So this negative magnetoresistance happens at E parallel to B. E parallel B means that you have no Lorentz force. Now, what we usually measure magnetoresistance, that you apply a current this way, you have magnetic field this way, right? The electrons will have been pulled to the sideway because Lorentz force is acting on it, and it will have this helic motion over there. That increases the trajectory of the path of electrons. That gives you magnetoresistance, right? But in the Clark sense, if you had E and the B's straight parallel together, there's no Lorentz force exerted on the charged particles over there, right? Then there should see no resistance, no change of resistance, right? However, this one tells that you will have negative magnetoresistance, and it's because of the chiral magnetic effect. I will tell you the formulation of that one. Okay. Oh, this one's complete that. Now I'm going to tell you what actually happened over there. Here I show you is that is a Weyl semimetals or Dirac semimetals. If you apply it in the magnetic field, this one is also dead. Yeah. Okay. I actually probably have ones. But well, anyway, to look at the left figure, top left figure there, in the magnetic field, right? You have a lower Landau levels, but if the band is linear dispersion of that, you will have linear bands. And right-handed one, I show the yellow ones, and left-handed ones, I show the green ones over there. They all have the different bands, right? That's on a linear band over there. And there's equal chemical potential. There's nothing change over there. And because spin the same, okay, the one is have to move forward, the other one is backward. That's what a left-hand and right-hand means, right? So you have the one occupy a different band there. Now, if you apply the electric field along the momentum direction, parallel K, what happened? The right-hander will move up, right? Left-hander will move down, right? Because that's got the same direction as the momentum if it's positive charge. And the other one goes down. This will create a chiral chemical potential. Now, if you have a chiral chemical potential for a charged particle, what happened? There's charge pumping mechanism started. Okay, let's see. Okay, hope this one works now. So this will cause a chiral pumping mechanism. We call it charge pumping. So this chiral potential will result in a charge motion this way. Now, in the momentum space, I showed it here. Right-handed ones, because this one is right-handed nodes over there, the chiral charge will move this way, and the left-handed will move down. On the surface, you lost chiralities to become Fermi arc here. So you have the motion of this one, and it's called Weyl ARPES. Okay. All right, so now with that, I'm going to give you two quick view of the equations. What is smoking gun there? We know that if your E dot B is non-zero, you provide a chiral source over there, and you have chiral chemical potential, and straightforward coming from this relativistic quantum field theory. And you have two processes there. One is that you have the chiral anomaly that generate this imbalance over there. E dot B is non-zero. And the other one actually try to flip the chiralities. And this is the bad part of that. Okay? If the chirality got flipping over there, and you were characterized by the chirality changing scattering time over there, and it's opposite to the generation of the chiral charge by the E dot B over there. Then you solve these equations, you end up with this formula. Okay, this is tell you what is the chiral chemical potentials, and you can compute that. You put this one into this chiral magnetic effect formula, you end up this equation. This is the chiral magnetic effect induced current proportional to some conductivity times E, and this conductivity, you can write it in case of B parallel E in this way. So now smoking gun here is this. This chiral conductivity is proportional to the B squared. Okay, that's enormous over there. That means if you apply more magnetic field, you draw more current. And it's a steady. It's not like Faraday's electricity generator. You have to change the flux to get the current. This is not. You just have a steady magnetic field. It's like a direct C. You have a lot of chiral fermions there, and you just pull the current out of it. It's a mind-boggling thing over there. But experimentally, you actually measure is the total conductivity, right? You measure total resistance. You still have regular quasi-particles happen there. So this is two terms you measure. This is the ohmic conductivity and this chiral magnetic effective part. But fortunately that if you E dot B, if magnetic field is parallel to the electric field, this one shouldn't have nothing happens, right? Because there is no Lorentz force to it. But this one has the B squared dependence. That's what you're looking for. This is the smoking pump. And this is what we did. So we have this single crystal here, and it's very nice. This is the electron diffraction pattern to show the crystallinity of this one is excellent. Then you measure it as function of magnetic field, and you rotate the magnetic field. Okay, the current in this case is always applied along the chain direction, A direction over here. Now, if you see a very large magneto resistance here, in a normal sense, when its current is perpendicular to the magnetic field. Now, that's the case for the B parallel to the B crystal B axis, C axis, and this is parallel A. You will see that it's a moment. Now, if you blow this up, you will find that actually it's negative for B and E in the parallel directions over there. And this is enormous over there, okay? And you can actually fit it with the B squared dependence. And this is what we found, this quadratic field dependence over there. This is the fit based on the theory over there. There's a weak linear localization. This topological materials is a different story there. But you can fit it. And also, this is the parameters. This is the factors, and it's temperature dependent, and you can find out this temperature dependence right here. And all these parameters is coming from resistivity and ARPES, right? The electronic structure over there. So essentially, there's no fitting parameter. You will find that it's very nice. It's done. So we believe that we found this chiral magnetic effect is a called pentatelluride, and I'll put it in the archive just before the Christmas of 2014, and 3 months later, it shows up in many other systems. Those are the Dirac systems over there, sodium bismuth, cadmium arsenide, and this is the Weyl semimetals over there. This shows the tantalum arsenic, and all other things, phosphates, all showed up. So, well, we're happy. We thought we're the first one. Actually, we're not the first ones. Okay. So, and later on, we found that there's another paper that actually showed an indication of that. And it didn't get much of interest at the time. I guess they called it topology insulators. Didn't, as we call it, Dirac semimetals over there. And they actually see some of the anomalous chiral anomaly in transport behavior of that one. So, later on, actually, this chiral magnetic effect can happen in many other materials, even though at the beginning you have a parabolic band. Even though at the beginning you don't have a direct band structure over there, you actually can observe that. The simple, this can be, this is reported here. The reason is that even though you have the parabolic bands, this is the semi-metal for the, this is the half-Oislers over there. This quadratic bands over here. But if you apply strong magnetic field, in this particular material there is very large G factor there. And this Zeeman energy will lead to the Y nodes because the band was split. Okay? This band was split two bands, and top of them split two, and this will result in band closing. And this band closing was found that is topological invariant. Okay, and that one can produce negative magnetism, and it's a huge deal to show that. Okay, so this one tell you that the current magnetic effect is much more general than what we see in the direct semimetals, as long as you can produce a wire nodes or direct nodes. But it's always in the wire nodes because in the magnetic field, you break time reversal symmetry already. And the other thing is that they tell you that these characters actually can be observable at room temperatures. And this is one of the recent experiments to show to measure this diffusion ends, chiral diffusion ends. The idea is that if you have regular scattering there, and if you put a contact here, measure apply electric field and measure the voltage, measure the current here, and that's what usually localized, right? That's a localized effect over there because that's you're driving the electrons there. But what happened for the chiral particles? It turns out the chiral particle can diffuse a much longer time. The reason is that they try to preserve their chiralities, okay? And it's protected, okay? And this chiralities, and they found this distance can be a few microns, okay? And this behavior was also found that happened at temperature up to 300 K. That's basically you will have a room temperature chiral magnetic effect. They call it chiral charging, pumping behaviors over there. So this one is another recent example to show you the detection manipulation of this chiral wire fermions by the optic approach. Now you can also couple these wire nodes or the behavior of that with optic approach. Okay, if you have circular polarized light here shining on a tandem arsenic, this is a wire semi-metal over there, you can produce a directional current, and this is due to that chiral effect over there. So in this sense, this is different ways to pumping. Okay, and I have told you that we can do that electrical control this wire nodes over there. You provide E dot B is non-zero, you can produce a chiral chemical potential, right? That result in charge pumping over there. And you can do the similar ways with optical, but here you have to use polarized light, okay? And you can do that. So most recently, we were looking at something even more. It's the AC chiral magnetic effect. The idea is this way. Now, if you have a chiral magnetic material here, okay, and you apply the bias here, and this is the DC magnetic field along this direction. Now, E applied here is also in the same direction here. Essentially, you provide a chiral source of that, right? And you also, in this field, you will be able to have a charge. The right-handed one goes forward, and left one goes on the other part of the face over there, and it's caused a charge separation. Okay, and the most important thing here that if my the frequency of this electric field is high enough over there and beat the chiral flipping rate, okay, this wave, the chiral magnetic wave, actually could transfer in a much longer distance and without resistance, right? Because the chirality conserved unless you flip the chirality over there. Okay. So this can provide ways to, I say the wire nodes is because they are protected by the conserve the chirality. It's quite robust and it could have some use for the delivery of quantum informations of that. Okay, now I think I'm going to summarize that. So I hope in this talk, in this colloquium there, I've tell you that the chiral magnetic effect was actually observed in the condensed matter now. And the chiral magnetic materials have opened a possibilities to study the quantum dynamics of relativistic field theory in the condensed matter experiments now. Okay, and the goal for our going forward as experimentalists is that try to understand chiral fermion transport behavior. Right now, I didn't tell you anything about the chiral flipping, right? And actually, this is the problem over there. And actually, because it's always scattering. The good news is that because it's not a regular particle scattering, right? You can just happen all the time, and it's very easy to flip it, to scatter. But for chiral particles, that you have to change the chirality, okay? So because they are on a separate wire nodes over there, it takes a large momentum transfer. Right? So that's why it's difficult to flip it. But it does flip, right? So the question is that what is the parameters control the flipping of the chiral particles over there, and can we control it? In that sense, to say that can we harness the power of chiralities and to develop a new route toward a non-dissipative transport of charge. So that's our dream over there. And with that, I thank you for attention.
Questions? Yes, Jim?
Yeah.
Are people trying to make films of these materials at this stage?
No, for this ones, this is a very good question, right? For the films, very thin films, it's not 3D because that's become a topology insulator there because then you lost chirality, it's not good. But you can get to, for instance, the condensed, if we get to like 100 nanometer over there, and it still follows the 3D behaviors. But if you look at the monolayer or something, then there's no chirality there. So the film it's not work for this particular case.
Is that what's necessary to kind of really harness it? Or?
Yes, well, if it's a single monolayer topology insulator, you probably already have edge state to do the job, right? But if you want to have the whole bulk do the conduction without dissipations, and then you go a little thicker of that one, you go into the 3D transition. So people can study this transition from the topological insulator to the Dirac semimetals by simply tuning the thickness of the samples. Okay.
Okay, go on.
Hi, Jeff.
What is the typical resistivity at room temperature and also at 10 degrees Kelvin?
Okay, that's a very good question. Actually beats me. Because this semimetals, because its carrier density is so low, so actually it's not good metal. So resistivity is a micro-ohm centimeter range.
Micro-ohm centimeter?
Oh, no, milli-ohm centimeter. I'm sorry, micro-ohm, that's a good metals. Milli-ohm centimeter, that's why most of the topological materials are the semi-metal, semiconductor of the thermoelectric. They are really not the good metals in there. So right now we're saying, oh, I can drop the resistance by a factor of 10, right? People are saying, so what? Right? You're still not beating the best metal yet, right? In that sense. So in a very low temperature over there, we can get the resistance down to, for instance, the cadmium arsenic, because that's a pretty low resistance to start with, a very high mobility. You can get to the tens of micro-ohm, but still not low enough. So, but the important thing is, if you apply magnetic field, that stuff keep going down. Okay.
Related to James' question,
Yeah.
can you actually make epitaxial thick films?
Yes, not in the condensed penetrator, which we didn't work, but on the other system over there, for instance, a tin telluride and other, I actually list a couple of them, right? Weyl semimetal, Dirac semimetal. Yes, you can make it, and it's very nicely, because those are most of the cubic systems. It's very easy to do. And also the one other thing is that you can use the strains to tune the material, because this electronic band structure is very sensitive to lattice constant. You can change the strains a little bit of that. You can actually induce the system to the topologies, to the Dirac semimetal, to the strong ones over there. So yes, it's possible to use the film to do that epitaxy.
Sean, can I have one more question?
Yes. Yeah.
So in the transmission line
Yeah.
storage,
Yeah.
superconducting,
Right.
superconductor storage,
Yeah.
and what is the state-of-the-art high temperature superconducting wires, and what's the current carrying capacity nowadays?
For the superconductors right now is actually you can make it into a very large, in terms of storage, right? We can make 30 Tesla ones. It's just too expensive, the problem. And you can carry the current density of that ones is, you can get to 10 to the 7th ampere per centimeter squares at 1 Tesla at 30 Kelvin. 77, not quite there. We can get 5 to 6 times 10 to the 6 ampere per centimeter square at 77.
Bismuth oxides?
It's a YBCO.
YBCO.
Bismuth ones actually, it's not that good. You know, YBCO is much more robust because it's more 3D. The bismuth stuff more 2D. Actually, the vortex just move around. It's very difficult.
Has this been commercialized?
Oh yeah, yeah. The tape is commercialized, and you can buy it. Actually, I have a program working with American Superconductors, and they sell a lot of. They call it million meters of wires, and they actually is commercial available.
Thank you.
Yeah.
So 2 questions.
Yeah.
One is, can you actually apply the strain and effector lattice on these bulk
Yes.
crystals?
Yeah.
Yeah, no problem.
No problem. That's
Okay.
actually, the crystal is pretty soft.
Nice. Good. Another thing is, do you have any idea of the frequency of this AC field, or it's just,
Yeah.
you know, effect is linearly proportional to, yeah?
Yeah, that's a good question. Actually, we have worked quite diligently to find out what's the frequency, right? It turns out that frequency is pretty high. That's because of the semimetal. You can calculate based on that small tiny gamma or nonlinearity of that. The calculation shows that the AC frequencies, where you want to beat Coriolis frequency rate, is in close to hundreds of gigahertz to terahertz. So that is, on the other hand, itself can be a terahertz emitters. So that would be interesting to see.
I actually have a question about contact. So when we think of the simplest system where anomalous transport is present, this would be, say, one-channel quantum wire or equivalently a quantum hole bar, and we know that in the wire itself there is no dissipation whatsoever. But the resistance of the wire will actually be pretty high because there is a quantum limit on the resistance of contacts at some 20 kilo ohms.
Yes.
So I wonder what would contacts do here? Is there any similar limit, or you can really go to arbitrary high conductance?
Yeah, that's a good question over there. Right now, that overall resistance is high, right? So the contact resistance is not a problem because you are high. But once you come to the very low resistive levels, your contact resistance becomes a problem, right? So, but contact resistance problems it's for long distance ones. But however, something we're doing right now is that we can actually make a superconductor contact with it. So we got the contact point, at least we can using superconductors to make joints of that, and it's possible for that. So did I answer your questions? I think so, yeah. Okay, thank you.
Okay, I have a question.
Yeah.
Thank you, Dima. So let's say I pretended to be Senator Jack Reed from Rhode Island.
All right.
And I'm reviewing Brookhaven's program.
Right.
So you are now telling us that you have found a non-dissipative charge transport mechanism in solid state. I agree.
Yeah.
That's great. Is it possible to make a wire out of this?
Not now. Okay. So this is a fair question. Okay. That's actually it's a very good one. So no, we don't see that. Be quite frank with you. I don't see this one as a way for a large scale bulk type of current transport mechanism over there. Okay. Because this is hard. But however, this one is good. I think it's for the quantum informations over there. And if we have a CPUs interconnect in the order of a few micron, even less of that, that will work.
So in federal agencies, you guys belong to Department of Energy, right?
Yeah.
Did they do quantum information as well?
That's getting very popular, and that's encouraged. It used to be that quantum information stuff is more of a DARPA's, DOD's program. Now they are encouraging us to see the broader pictures of how we're going to apply some of the facility expertise to help with the quantum informations. And here the states, the topology states over there could be helpful to do that.
All right. Okay. Thank you. So we'll send in proposals to DOE then.
Okay. Yeah.
Let's thank Dr. Lee again.
Thank you. Yeah.
Great talk.
Okay.
We had a disaster.
No, it's not disaster. It's just
Both of these. Okay. So
yeah.